Hello and welcome to the Unit 5 Linear Momentum Conceptual Review by the Irvine High School Physics Club. You can join us on our Mind at Phys IHS. Let's get started. Alright, so today's lecture is going to be slightly shorter than usual because momentum kind of builds upon a series of other topics that we've already learned, like kinematics and forces. So, what is linear momentum? Well, we usually express it in P in equations. It's a physical quantity that describes an object's motion. You can use it in a variety of situations to describe like how hard an object's moving, if you don't want to use acceleration, because the formula for momentum is mass times velocity, or mv. And however, if we do want to connect this to a force exerted over a short amount of time, which say would accelerate an object from some initial velocity to some final velocity, then we can express that there's a name for this term, and it's called impulse. Now, impulse is equal to two things. It's equal to the force exerted over a period of time. Now, notice that this force has to be the only force on the object at the moment, and it has to be constant, meaning it's not going to change. So we have that quantity, and it's also equal to the change in linear momentum. So if we're looking at two stages of time before and after the object force is being exerted on the object, we're going to have a change in momentum, right? Which is mv in final minus mv initial. That's typically the force would be exerted over a very short time interval, but since we have this equation, you can modify it based on what the problem is asking. Another important aspect to consider is that both impulse and momentum are going to be vectors, right? So you're going to have to include positive and negative signs. So be careful when a question asks you, for example, the magnitude of impulse or the magnitude of momentum, because if they're asking about magnitude, then it has to be positive. But sometimes it can be negative, and you have to make sure you take that into account. Also, notice that the product of mv, again, is linear momentum, and it represents a quantity of motion for the object. You can use it to kind of describe physically what is going on. Like if two balls, one's very heavy, one's very light, are rolling at the same velocity, you're going to say, oh, well, if the bigger ball hits you, it's going to be a much harder impact than the smaller ball. And that's because it has greater mass. Similarly, you can use the velocity argument. If one's moving much faster, but they both share the same mass, but one's moving much faster than the other one, you're going to have a greater momentum, right? And obviously, you don't want to get hit by the faster one. Rather, the slower one would be less hurtful, less painful. And another final tip to consider is, what is a system where momentum is fully conserved? So obviously, as we learned, conservation of momentum is sometimes really useful, especially for collisions. One-dimensional and two-dimensional, doesn't matter, but the system we always have to take into account, right? The system is just going to be the two different objects, or however many objects are being involved in the collision. We know this is a system where momentum is conserved because there's no net external force exerted on the object. And that's a very handy way to calculate the final velocities, the final speeds, stuff like that, is some other information that the problem will probably ask you to find. So overall, momentum is really useful. Make sure you use conservation of momentum when you see it, when there's no net external force on the system that you're choosing, which is likely two or more objects, right, involved in the collision. Now let's take a look at the center of mass, which usually appears in problems because when you calculate conservation of momentum, it's usually, although we don't typically say it or mention it, it's typically about the center of mass of the system. Now, this is very special because it's going to be the point where the linear momentum of either side of, say, an object is going to be equal. So it's going to be essentially where the mass is concentrated at a center, if there were to be a center. Right. Now, obviously, everything's geometric, everything's abstract, but if we were to place a physical point, it would be the center of mass, where both sides have equal mass, so it's perfectly imbalanced. Now, it's not necessarily going to be the middle of an object, keep in mind, because the mass might be distributed in a weird way, right? So, for example, for baseball bats. Well, when you take a look at a bat, you obviously know that the mass is not going to be equal if you hold it by the middle. And you can actually try this on different objects by balancing them on your finger and trying to kind of use trial and error and identify which point would allow both sides to be in balance. So obviously for a bat, in the case of a bat, the bases would be, well, the handle would be a lot lighter, just thinking intuitively, and the end would be heavier, right? So if you want to find a balance, you would probably be putting your finger closer to the end of the bat rather than the handle of the baseball bat, right? Because it's more of the mass is concentrated next to the end. So that's where the center of mass will be closer to. At least that much you know. So it's not going to be at the exact center of the bat. And if you want to express center of mass in a formulaic sense, it's going to be just the sum of all the masses, all the mass points, times how far they are from a given origin. Now, this is important because you can define the origin. You can define any point to be like a 0 point. The only thing with that is if you're defining it that way, the eventual center of mass, which you end up calculating, its distance is going to be relative to that 0 point. So just make sure you're keeping track of, if you ever do any COM calculations, that you know where, or at least you're keeping track of where your center is, or where your origin is. So just make sure everything is all relative to the origin. And if this kind of some notation of expressing center of mass doesn't really help you identify it, or doesn't help you that much visually, you can also think of it as the weighted average of distance from a singular point, returning again back to this origin notion that we know of. So overall, the center of mass, it's going to be particularly helpful because in collisions, right, the center of mass will never move. So when you use conservation of momentum, that you're actually implicating the fact that the center of mass does not move left or right. And that's why you're able to use center of mass in the conservation system. As always, thank you for your viewership. We greatly appreciate it. Make sure to join us on Remind if you haven't already at PHYSIHS. And yeah, that's it. So thank you so much. Have a great day and see you for our Unit 6 lecture.